Imagine a world where oceans of molten rock churn beneath a sky of perpetual fire, its surface screaming with volcanic eruptions and temperatures hot enough to melt steel. Now picture this hellish realm recently revealed by NASA's James Webb Space Telescope, not just existing, but breathing. Scientists have detected an eerie, thick atmosphere swirling around this lava planet, defying expectations. How? Spectroscopy hints at gases clinging to its scorching surface, possibly shaped by relentless volcanic activity and extreme pressure. The discovery shakes assumptions about planetary formation, suggesting even the most hostile worlds might harbor complex chemistry. But here's the twist: the atmosphere's composition hints at something unexpected, maybe not just volcanic steam, but traces of compounds that hint at processes eerily similar to Earth's. This isn't just a distant rock, it's a cosmic puzzle, forcing us to rethink what makes a world alive and whether life, in any form, could thrive in the most punishing corners of the universe. In the vast expanse of our universe, where stars burn and planets orbit in silent harmony, a new discovery has shaken the foundations of planetary science. NASA's James Webb Space Telescope, the most advanced observatory ever built, has revealed an atmosphere on a planet so extreme it's often called a lava world, a hellish world where temperatures could melt rock and conditions are so hostile that even the idea of life seems impossible. But what makes this discovery so astonishing is not just the existence of an atmosphere on such a planet, but the strange composition of that atmosphere, hinting at processes that defy our current understanding of planetary formation. This is the story of how a single telescope, peering billions of light-years away, has uncovered a mystery that could rewrite what we know about the cosmos. The planet in question, named K2-146b, is a hot super-Earth, a rocky world larger than Earth but smaller than gas giants, orbiting a star much smaller and cooler than our Sun located approximately 180 light-years from Earth. It's part of a binary star system, meaning it orbits two stars instead of one. This unique setup creates an environment of extreme instability. One side of the planet is perpetually bathed in intense radiation, while the other is shrouded in eternal darkness. The temperature differences are so drastic that the planet's surface is believed to be a molten wasteland, with lava oceans flowing beneath a thin crust. Such conditions make K2-146b one of the most inhospitable worlds ever discovered, a place where even the concept of a stable atmosphere seems impossible. Yet, the James Webb Space Telescope has found that this planet does have an atmosphere, and it's not the kind of atmosphere we expect. The telescope's instruments, designed to detect faint light from distant worlds, captured the faintest signals of gases trapped in the planet's atmosphere. Among these gases are water vapor and carbon monoxide, substances that, on Earth, are closely tied to life and geological activity. But on K2-146b, these molecules exist in a state that defies our understanding. Water vapor, for instance, is typically associated with cold environments, where it can condense into clouds or ice. Here, it's present in a form that suggests it's being continuously replenished, perhaps by volcanic activity or other high-energy processes. Carbon monoxide, meanwhile, is a byproduct of combustion and is typically found in environments with active geology or atmospheric chemistry. Its presence here raises questions about how such a molecule could persist in a world where temperatures are so extreme that even metals would melt. The discovery is perplexing because it challenges our assumptions about how atmospheres form and survive on such planets. Most exoplanets with atmospheres discovered so far are either gas giants or icy worlds, and their atmospheres are shaped by their unique conditions. K2-146b, however, is a rocky planet with a surface that should be too hot to sustain any stable atmosphere. The James Webb's findings suggest that despite these conditions, the planet somehow maintains a thin layer of gas, possibly held in place by the gravitational pull of its host stars or by the planet's own magnetic field. But how this atmosphere is sustained remains a mystery. Scientists are now scrambling to understand the mechanisms that could allow such a planet to retain an atmosphere in an environment where even the air should be stripped away by intense stellar radiation. One theory is that the planet's atmosphere is being constantly replenished by volcanic activity. On Earth, volcanoes release gases like water vapor and carbon dioxide into the atmosphere, and similar processes might be occurring on K2-146b. However, the presence of carbon monoxide is particularly puzzling. On Earth, carbon monoxide is a byproduct of incomplete combustion, often associated with industrial processes or wildfires. In the absence of life, Its presence on K2-146b suggests a different kind of geological or chemical activity. Some scientists speculate that the planet's atmosphere could be the result of chemical reactions between molten rock and the planet's interior, creating a unique mix of gases. Others propose that the planet's atmosphere might be influenced by the presence of its binary star system, where the gravitational tug of two stars could create complex weather patterns or even influence the planet's magnetic field, allowing the atmosphere to persist. The implications of this discovery are profound. For years, scientists have debated whether rocky planets like K2-146b could even have atmospheres, let alone complex ones. The James Webb's findings suggest that such planets are more capable of retaining atmospheres than previously thought, which could have far-reaching consequences for our understanding of planetary formation. If a planet as hot and volatile as K2-146b can maintain an atmosphere, it opens the door to the possibility that other similarly extreme worlds might also have atmospheres, some of which could even be habitable. While K2-146b itself is too hot for life as we know it, the discovery raises the tantalizing possibility that other planets in similar conditions might have atmospheres that are more temperate or even conducive to life. Moreover, the presence of water vapor on K2-146b challenges our understanding of how water behaves in extreme environments. On Earth, water exists in three states: solid, liquid, and gas, depending on temperature and pressure. But on K2-146b, the temperatures are so high that water would typically exist as a gas, yet the telescope detected it in a form that suggests it's being continuously cycled through the planet's environment. This could indicate that the planet has a dynamic system of atmospheric processes, where water vapor is being released from the planet's interior and then somehow retained despite the intense heat. Such a system would require a delicate balance of geological and atmospheric factors, further emphasizing the complexity of this world. The James Webb Space Telescope's ability to detect these gases is a testament to the power of modern astronomy. Unlike previous telescopes, which struggled to capture faint signals from distant worlds, the James Webb's advanced instruments allow scientists to peer into the atmospheres of exoplanets with unprecedented precision. This discovery is a milestone in the field of astrobiology, as it demonstrates that even in the most extreme environments, there is potential for complex atmospheric phenomena. It also highlights the importance of continued exploration, as each new discovery brings us closer to understanding the full diversity of planets in our galaxy. As scientists continue to analyze the data from K2-146b, they are uncovering new questions that could redefine our understanding of planetary science. The presence of an atmosphere on such a hellish world challenges existing models and forces us to reconsider the conditions under which planets can form and sustain atmospheres. It also raises the possibility that other planets, even those in the most extreme environments, might have atmospheres that are more complex than we ever imagined. While K2-146b itself is a world of fire and fury, its atmosphere serves as a reminder that the universe is full of surprises, and that even in the most inhospitable corners of space, there is potential for discovery. The James Webb Space Telescope has opened a new chapter in our exploration of the cosmos, and the story of K2-146b is just the beginning of a much larger narrative, one that continues to unfold as we look deeper into the universe. The quest to understand the universe has always been driven by the question, what lies beyond our own world? For decades, scientists have looked to the stars, searching for planets that might harbor life, or at least, the conditions that could make life possible. But the universe is vast, and most exoplanets are so distant that even the most advanced telescopes struggle to peer through the cosmic void. Enter the James Webb Space Telescope, a marvel of engineering and ambition, designed to peer into the infrared spectrum and unlock secrets hidden from previous generations of observatories. Its mission was clear: to study the formation of galaxies, the birth of stars, and the atmospheres of distant worlds. Yet, what it has revealed so far has pushed the boundaries of our understanding, challenging assumptions about what planets can be and what they might hold. One such discovery, made possible by Webb's unparalleled sensitivity, has captivated scientists and the public alike: the detection of a strange, unexpected atmosphere on a planet so hostile it resembles a hellish lava world. How did this happen? Let's follow the journey of discovery, step by step, from the telescope's design to the moment scientists realized they had glimpsed something extraordinary. The James Webb Space Telescope is not just a telescope, it's a technological revolution. Launched in 2021, it was built to overcome the limitations of its predecessors, like the Hubble Space Telescope, which could only observe invisible and ultraviolet light. Webb's primary innovation lies in its ability to detect infrared light, which allows it to peer through the dust and gas that obscure young stars and distant planets. This capability is crucial for studying exoplanets, as the light from their host stars is often too bright to detect the faint signals of their atmospheres. Webb's mirror, nearly 3 times larger than Hubble's, and its advanced instruments, such as the near-infrared spectrograph, NIR-SPEC, and the near-infrared camera, NIR-CAM, are engineered to capture the faintest glimmers of light from billions of light-years away. But even with these tools, the task of finding an atmosphere on a distant planet is no small feat. It requires not only cutting-edge technology but also a deep understanding of how light interacts with matter. The process of detecting an exoplanet's atmosphere begins with a technique called transit spectroscopy. When a planet passes in front of its host star, it briefly blocks a portion of the star's light. During this transit, the star's light filters through the planet's atmosphere, and certain wavelengths are absorbed by gases in the atmosphere. By analyzing the subtle changes in the starlight, scientists can deduce the composition of the planet's atmosphere. However, this method demands precision. The planet's atmosphere must be thick enough to leave a detectable imprint, and the star's light must be stable enough to measure the tiny variations. For a planet like the one in question, a super-Earth with surface temperatures hot enough to melt rock, these conditions are extreme. The planet's atmosphere, if it exists, would be subject to intense stellar radiation and high temperatures, making it difficult to detect. Yet, Webb's infrared sensors are uniquely suited to this challenge, as they can detect the thermal glow of molecules in the atmosphere, even in the presence of intense stellar light. The journey to this discovery began years before Webb's launch. Scientists had long suspected that some exoplanets might have atmospheres, but confirming their existence required a telescope with the sensitivity and resolution to capture the faintest signals. The target planet, which scientists have dubbed a lava world due to its extreme surface temperatures, was identified through earlier observations by ground-based telescopes and the Hubble Space Telescope. These initial studies hinted at the presence of a dense atmosphere, but the data was inconclusive. The planet's host star, a red dwarf, is known for its violent flares and strong magnetic fields, which can distort the light from its planets. This made the planet an especially difficult target, as any atmospheric signal would be drowned out by the star's activity. Yet, the potential reward was immense. If the planet had an atmosphere, it could provide insights into how such extreme worlds form and evolve. When Webb began its observations, the team focused on the planet's transit events, carefully timing each pass to ensure optimal conditions. The telescope's instruments were calibrated to capture the faintest changes in light, and the data was collected over multiple transits to build a robust dataset. The process was meticulous. Each observation required precise alignment with the planet's orbit, and the data had to be filtered to remove noise from the star's own variability. The team also had to account for the planet's proximity to its star, which meant the planet's atmosphere would be subjected to intense radiation, potentially altering its composition. Despite these challenges, the data began to reveal something unexpected. The absorption lines in the starlight suggested the presence of gases that did not fit the expected profile of a lava world atmosphere. Instead of the expected signatures of carbon dioxide or water vapor, the spectrum showed anomalies that hinted at the presence of other elements, possibly even compounds that could indicate complex chemical interactions. The analysis of the data was a collaborative effort, involving scientists from around the world. The team used advanced computational models to simulate the possible compositions of the atmosphere, comparing the observed data with theoretical predictions. What they found was both surprising and intriguing. The atmosphere seemed to contain molecules that should not exist under the planet's extreme conditions. Some of these molecules, like certain hydrocarbons, are typically associated with cooler, more temperate environments. The presence of such compounds in a planet so close to its star raised questions about the planet's formation and evolution. Could the atmosphere be the result of volcanic activity? Or was it a remnant of a different kind of planetary history? These questions underscore the complexity of the discovery, as the data suggested a world that defied conventional expectations. The confirmation of the atmosphere's existence was a moment of triumph for the scientific community. But the process of verification was far from simple. The team had to rule out alternative explanations for the observed signals. Could the data be an artifact of the telescope's instruments? Could the star's activity have distorted the measurements? To address these concerns, the team conducted multiple checks, cross-referencing the data with observations from other telescopes and simulations of the planet's environment. The consistency of the results across different methods gave confidence that the atmosphere was real. The findings were not just a confirmation of the planet's atmospheric presence but also a glimpse into the dynamic processes that shape such extreme worlds. The atmosphere, though strange, provided a window into the planet's past and present, offering clues about its geological and atmospheric history. The implications of this discovery extend far beyond the specific planet in question. It challenges our understanding of how atmospheres form and persist in extreme environments. For years, scientists have debated whether planets orbiting red dwarfs, like the one in this case, could maintain stable atmospheres. The presence of an unexpected atmosphere on this lava world suggests that such planets may be more complex and diverse than previously thought. It also highlights the importance of continued exploration, as the James Webb Space Telescope continues to uncover new mysteries in the cosmos. Each discovery, no matter how strange or unexpected, contributes to a broader picture of the universe, one that is as dynamic and unpredictable as the worlds it contains. The journey to this discovery was a testament to human ingenuity and perseverance, a reminder that even in the most hostile corners of the universe, there is always more to learn. Imagine a planet where the surface is molten, with temperatures so extreme they could melt steel. Now, imagine that such a world has an atmosphere, something we never thought possible. This is the astonishing discovery made by NASA's James Webb Space Telescope, revealing a strange atmosphere on a hellish lava planet. But how did this happen? And why does it matter? To understand this, we need to dive into the science of planetary atmospheres, the conditions that shape them, and what this discovery tells us about the universe we live in. Planets with atmospheres are typically associated with cooler, Earth-like worlds, places where liquid water can exist. But the James Webb Telescope has shown us that even in the most extreme environments, planets can still retain atmospheres. This lava planet, with surface temperatures that could melt rock, defies our expectations. Its atmosphere, though thin and volatile, contains elements that challenge our understanding of how such worlds form and evolve. By studying this anomaly, we're not just learning about this one planet, we're gaining insights into the broader processes that shape planets across the galaxy. Atmospheres form through a delicate balance of physics and chemistry. On Earth, our atmosphere is a result of volcanic activity, tectonic processes, and the presence of liquid water. Gases like nitrogen, oxygen, and carbon dioxide are trapped by gravity and shielded from the vacuum of space. But on a lava planet, the conditions are utterly different. The surface is a molten ocean of rock, constantly shifting and erupting. Volcanic activity would release gases like carbon dioxide, sulfur dioxide, and water vapor into the atmosphere. However, the extreme temperatures would make it difficult for these gases to linger. Most would escape into space or condense into vapor. Yet, the James Webb Telescope has detected a thin but persistent atmosphere, suggesting that some process is keeping it from vanishing. The key lies in the planet's gravity and the balance between atmospheric retention and escape. A planet's ability to hold onto an atmosphere depends on its mass and the speed at which gas molecules move. On Earth, gravity is strong enough to keep gases like nitrogen and oxygen from escaping into space. But on a lava planet, the gravity is likely weaker, and the extreme heat would cause gas molecules to move faster, increasing the likelihood of escape. Yet, the presence of an atmosphere suggests that some mechanism is counteracting this. One possibility is that the planet's volcanic activity continuously replenishes the atmosphere, creating a dynamic equilibrium. Another is that the atmosphere is composed of heavier gases that are less likely to escape, such as carbon monoxide or sulfur compounds. These gases might form through chemical reactions between volcanic emissions and the planet's surface, creating a self-sustaining cycle. The James Webb Telescope's discovery of this atmosphere is significant because it reveals that even in the most extreme environments, planets can develop complex atmospheric systems. This challenges the assumption that atmospheres are only possible on planets with Earth-like conditions. Instead, it suggests that a wide range of planetary environments can support atmospheres, shaped by unique combinations of volcanic activity, gravity, and chemical processes. By studying this lava planet, scientists can refine models of atmospheric retention and gain a better understanding of how different planets evolve over time. These insights could also help us predict the atmospheres of other exoplanets, even those that are too distant or too hot to study in detail. But why does this matter? The study of exoplanet atmospheres is crucial for understanding the diversity of worlds in our galaxy. While we've long searched for habitable planets, this discovery shows that even planets that seem inhospitable can have complex atmospheric dynamics. This expands our definition of what a planet can be and highlights the importance of studying a wide range of environments. Moreover, the techniques used to detect this atmosphere, such as infrared spectroscopy, have broader applications. The James Webb Telescope's ability to analyze light from distant planets allows scientists to identify the chemical signatures of atmospheres, even in the most extreme conditions. This technology is paving the way for future discoveries, including the detection of potential biosignatures on other worlds. The implications of this discovery also reach into the field of planetary formation. How do planets like this form? Are they common in the universe, or are they rare anomalies? The presence of an atmosphere on a lava planet suggests that planetary systems can produce a wide variety of worlds, from rocky, molten planets to gas giants with thick atmospheres. This diversity challenges existing models of planetary formation, which often focus on Earth-like planets. By studying these extreme worlds, scientists can refine their understanding of how planets form and evolve, shedding light on the processes that shape entire planetary systems. Another fascinating aspect is the role of volcanic activity in shaping atmospheres. On Earth, volcanoes release gases that contribute to the atmosphere, but on a lava planet, the scale of volcanic activity would be immense. The constant eruptions could create a feedback loop, where volcanic emissions replenish the atmosphere while also influencing its composition. For example, sulfur dioxide and carbon dioxide could react with the planet's surface, forming new compounds that alter the atmospheric chemistry. This dynamic interplay between volcanic activity and atmospheric composition could create a unique environment, one that is both volatile and complex. Understanding these processes could help scientists model the atmospheres of other planets, including those that may have once been habitable but are now inhospitable. The discovery also raises questions about the long-term stability of such atmospheres. How long can a lava planet maintain its atmosphere before it is stripped away by stellar winds or internal processes? The James Webb Telescope's observations suggest that the atmosphere is thin but persistent, indicating that some balance is being maintained. However, the planet's extreme conditions mean that this balance is fragile. Over time, factors such as increased volcanic activity, changes in the planet's magnetic field, or interactions with its host star could alter the atmosphere's composition or even cause it to dissipate entirely. Studying this planet's atmosphere provides a glimpse into the transient nature of planetary atmospheres and the challenges of maintaining them in extreme environments. Beyond the scientific implications, this discovery has profound philosophical significance. It reminds us that the universe is full of surprises, and that our understanding of planetary systems is still evolving. The idea that a planet with a molten surface can have an atmosphere challenges our assumptions and expands our view of what is possible. It also underscores the importance of continued exploration, as each new discovery has the potential to reshape our understanding of the cosmos. By studying these extreme worlds, we're not just learning about their unique characteristics, we're gaining insights into the fundamental processes that govern the universe. In conclusion, the James Webb Space Telescope's discovery of a strange atmosphere on a hellish lava planet is more than just an observation, it's a window into the vast and complex tapestry of planetary science. It reveals that even in the most extreme conditions, planets can develop atmospheres shaped by unique combinations of physics, chemistry, and geological activity. This finding challenges existing models, expands our understanding of planetary formation, and highlights the importance of studying a wide range of environments. As we continue to explore the universe, discoveries like these remind us that the cosmos is full of mysteries waiting to be unraveled, and that every new insight brings us closer to understanding our place in the universe. For decades, scientists have been peering into the cosmos, searching for signs of life beyond Earth. But the quest to understand exoplanets has taken a dramatic turn in recent years, driven by a series of groundbreaking missions that have expanded our view of the universe. the discovery of a strange atmosphere on a hellish lava planet, made possible by NASA's James Webb Space Telescope, is the latest chapter in a long story of cosmic exploration, one that began with the first whispers of planets beyond our solar system and has evolved through decades of technological innovation and scientific curiosity. To understand how we arrived at this moment, we must look back to the early days of exoplanet research, when the very idea of planets orbiting other stars was still met with skepticism. The first confirmed exoplanet, discovered in the 1990s, was a gas giant orbiting a pulsar, a dense stellar remnant. This finding, though surprising, opened the door to a new frontier, the study of worlds beyond our own. Yet, for years, these distant planets remained little more than dots of light, their secrets hidden behind the vastness of space. It wasn't until the late 1990s and early 2000s that scientists began to develop the tools to peer deeper, to analyze the faint signatures of atmospheres, and to glimpse the possibility of life elsewhere. The Hubble Space Telescope, launched in 1990, played a pivotal role in this transformation. While its primary mission was to study the universe in visible light, Hubble's ability to detect subtle changes in starlight as planets passed in front of their stars, transit spectroscopy, allowed scientists to begin mapping the chemical fingerprints of exoplanet atmospheres. These early efforts revealed the presence of gases like water vapor, carbon dioxide, and methane, offering tantalizing clues about the conditions on these alien worlds. However, Hubble's instruments had their limits. Its sensitivity was constrained by the size of its mirror and the challenges of observing in the infrared spectrum, where many key atmospheric signatures lie. Enter the Spitzer Space Telescope, launched in 2003, which operated in the infrared. Spitzer's ability to detect thermal emissions from planets allowed scientists to study the heat radiating from these distant worlds, providing insights into their temperatures and atmospheric compositions. Yet, even with Spitzer's capabilities, the data remained sparse. The true breakthrough came in the 2010s, with the launch of the Kepler Space Telescope. Kepler's mission was to survey a vast region of the Milky Way for planets in the habitable zones of their stars, regions where liquid water could exist. Over its 9-year operational life, Kepler discovered thousands of exoplanets, many of which were rocky, Earth-like worlds. This flood of data revolutionized our understanding of planetary systems, revealing that planets are common in the universe and that many of them orbit stars in configurations previously thought impossible. But while Kepler expanded our catalog of exoplanets, it couldn't directly analyze their atmospheres. That task fell to the next generation of telescopes, including the Transiting Exoplanet Survey Satellite, TESS, launched in 2018. TESS built on Kepler's legacy by focusing on nearby stars, enabling astronomers to study planets in greater detail. Its observations helped identify hundreds of new exoplanets, some of which showed promise for atmospheric analysis. Yet, even with these advancements, the detection of atmospheres remained a challenge. The key to unlocking this mystery lay in the development of more powerful instruments capable of capturing the faintest signals. Enter the James Webb Space Telescope, launched in 2021. With its massive mirror and advanced spectroscopic instruments, JWST represents a quantum leap in our ability to study distant worlds. Unlike its predecessors, JWST operates primarily in the infrared, where it can detect the faint thermal glow of exoplanets and the subtle absorption lines of atmospheric gases. This capability has allowed scientists to probe the atmospheres of planets in unprecedented detail, revealing the presence of molecules like water, carbon dioxide, and even complex organic compounds. But the discovery of a strange atmosphere on a lava planet marks a particularly striking milestone. Such planets, characterized by extreme temperatures and molten surfaces, were once thought to be devoid of atmospheres. The intense heat would have stripped away any gases, leaving behind a barren, rock-covered world. Yet, JWST's observations suggest otherwise. The presence of an atmosphere on this hellish world challenges existing models of planetary formation and evolution, hinting at processes that may have preserved or even generated atmospheric components despite the planet's extreme conditions. This finding is not just a scientific curiosity, it has profound implications for our understanding of planetary science. It suggests that the universe is far more diverse and complex than previously imagined, with planets exhibiting a wide range of atmospheric behaviors. Moreover, it raises new questions about the potential for life in extreme environments. While the lava planet in question is undoubtedly inhospitable, the discovery of an atmosphere on such a world underscores the importance of continued exploration. Each new observation brings us closer to answering fundamental questions about the nature of planets, the conditions that can sustain atmospheres, and the possibilities for life beyond Earth. The journey to this discovery was paved by decades of scientific ingenuity and technological progress. From the first exoplanet detection to the launch of JWST, each step has brought us closer to unraveling the mysteries of the cosmos. And as we look to the future, the lessons learned from these missions will undoubtedly shape the next era of space exploration, guiding us toward even deeper insights into the universe we call home. The James Webb Space Telescope has unveiled a discovery that challenges our understanding of planetary atmospheres. A distant exoplanet, scorching hot and covered in molten rock, has been found to possess an atmosphere, something that should be impossible under its extreme conditions. This finding raises more questions than answers. How could such a planet retain an atmosphere? What processes are at work here? And what does this mean for our understanding of planetary formation and evolution? These are the mysteries that scientists are now racing to unravel. The James Webb Space Telescope, with its unprecedented sensitivity and ability to peer into the infrared spectrum, has allowed us to detect faint traces of atmospheric gases around this hellish world. But the data it has returned is perplexing. The atmosphere is not what we expected. It lacks the heavy elements typically associated with volcanic outgassing, and its composition suggests a different origin story. This is not just a technical challenge, it's a fundamental rethinking of how atmospheres form and survive in the most extreme environments. Scientists are now grappling with the implications of this discovery, debating whether it's a rare anomaly or the tip of a larger, unexplored phenomenon. The atmosphere's presence defies conventional models, which predict that such planets would lose their atmospheres to the intense heat of their host stars. Yet here it is, defying expectations. What could be holding it together? Is there an unknown mechanism at play? Or is this a sign that our understanding of planetary atmospheres is incomplete? These questions are driving a new wave of research, as scientists across disciplines come together to piece together the puzzle. The James Webb Space Telescope's data is a starting point, but it's not the full picture. To understand this strange atmosphere, we need to look beyond the immediate observations. We need to consider the broader context of planetary science, the history of how atmospheres form, and the factors that might allow them to persist in such hostile conditions. One possibility is that the atmosphere is not a result of volcanic activity, as many had assumed. Volcanic outgassing is a common source of atmospheres on rocky planets, releasing gases like water vapor, carbon dioxide, and sulfur compounds. But the composition of this planet's atmosphere doesn't align with what we'd expect from such processes. Instead, it suggests a different mechanism, perhaps a combination of atmospheric retention and chemical reactions that we haven't yet considered. Another angle is the role of the planet's magnetic field. A strong magnetic field could shield the atmosphere from the erosive effects of stellar radiation, allowing it to persist despite the intense heat. However, the data doesn't provide clear evidence of such a field, leaving this theory in question. The absence of certain elements in the atmosphere also complicates things. For example, the lack of heavy metals like iron or magnesium suggests that the atmosphere may have formed in a different way, perhaps through the condensation of volatile compounds or the accretion of icy materials. But how could such materials survive on a planet with surface temperatures hot enough to melt rock? These are the kinds of questions that keep scientists awake at night. The James Webb Space Telescope has given us a glimpse into this enigmatic world, but it's not enough. We need more data, more observations, and a deeper understanding of the physical processes at play. This discovery is forcing us to reconsider long-held assumptions about planetary atmospheres. For decades, we've thought of atmospheres as the result of geological activity, volcanic outgassing, and the gradual accumulation of gases over billions of years. But this planet's atmosphere seems to defy those models. It's as if the planet itself is a puzzle, with pieces that don't fit the expected picture. Scientists are now exploring alternative theories, some of which are speculative but grounded in existing scientific principles. One possibility is that the atmosphere is a transient phenomenon, formed by a sudden event such as a massive impact or a burst of volcanic activity. Such an event could inject large amounts of gas into the atmosphere, creating a temporary layer that might persist for a time before being stripped away. However, the data doesn't provide clear evidence of such an event, and it's unclear how long the atmosphere has been present. Another theory suggests that the atmosphere is the result of chemical reactions between the planet's surface and its interior. For example, if the planet has a subsurface ocean or a layer of magma, chemical interactions could release gases that accumulate in the atmosphere. This would require a complex interplay between the planet's geology and its atmospheric composition, something that is still being studied. The challenge here is that we don't have direct measurements of the planet's surface or interior, so these theories remain hypothetical. The James Webb Space Telescope has given us a window into this world, but it's a narrow one. To fully understand the atmosphere, we need to look at the planet in greater detail, something that current technology may not yet allow. This is where the broader field of planetary science comes into play. Researchers are now turning to simulations and models to test the various hypotheses. By running computer simulations of different atmospheric conditions, scientists can see which scenarios are most plausible. These models take into account factors like the planet's distance from its star, its orbital characteristics, and the potential for atmospheric retention. However, even with these tools, the answers remain elusive. The data from the James Webb Space Telescope is a starting point, but it's not definitive. There are gaps in the observations, and some of the measurements are still uncertain. This is why the scientific community is so eager to see more data. Every new observation could shift our understanding, revealing new clues or ruling out certain theories. The discovery of this atmosphere is a milestone, but it's also a challenge. It's forcing us to think outside the box, to consider possibilities that we might have overlooked. This is the nature of scientific inquiry. Each discovery opens new questions, and each question leads to new avenues of research. The James Webb Space Telescope has given us a glimpse of a strange and fascinating world, but the full story is still being written. As scientists continue to study this planet, they are uncovering new layers of complexity. The atmosphere's existence is a testament to the resilience of planetary systems, but it also highlights the gaps in our knowledge. We know that atmospheres can form in a variety of ways, but this case is unique. It's a reminder that the universe is full of surprises, and that our understanding of it is always evolving. The debate over this discovery is far from over. Scientists are still discussing the implications, and new findings could change the direction of the research. What is clear is that this atmosphere is a puzzle, one that requires collaboration, creativity, and a willingness to challenge established ideas. The James Webb Space Telescope has provided us with a rare opportunity to study a world that was once thought to be inhospitable. But in doing so, it has also opened up new frontiers in planetary science. The questions it raises are as important as the answers it provides. And as long as there are unanswered questions, the search for knowledge will continue. This is the essence of scientific discovery: curiosity, perseverance, and the pursuit of understanding. The strange atmosphere on this hellish lava planet is just the beginning of a much larger story. As we look to the future, we can only wonder what other mysteries await us in the cosmos. The James Webb Space Telescope has given us a new tool to explore the universe, and with it, a new sense of wonder. The journey of discovery is just beginning, and the possibilities are endless. NASA's James Webb Space Telescope reveals a strange atmosphere on a hellish lava planet. This part of our deep dive into NASA's James Webb Space Telescope reveals a strange atmosphere on a hellish lava planet focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. NASA's James Webb Space Telescope reveals a strange atmosphere on a hellish lava planet. This part of our deep dive into NASA's James Webb Space Telescope reveals a strange atmosphere on a hellish lava planet focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.